we've looked at energy level diagrams and energy level transitions. We're now going to take that a step further and consider all of the energy level transitions that can occur. We saw at the end of the last video that when there are energy level transitions, they have different amounts of energy, and for any given atom, that means that when an electron falls from a higher to a lower energy level, it's going to have a discrete or a quantized amount of energy. And that term quantized basically just means that it's a specific amount. You can't get any just any amount. It's a very specific amount that will occur, and that's where the term quantum physics comes from. So we're dealing with specific amounts or specific quanta of energy. So that then means we can sort of start to look at each atom very specifically. Before we do that though, let's have a look at the energy of those photons that are going to be emitted. Now, again, mentioned in a previous video that we're not really going through this unit in its fullest depth. So this equation, I'm just going to state it, but there is a bit of a few interesting steps along the way that allowed us to understand this particular equation. The equation is basically just looking at the relationship between the energy of the photon and the frequency of the photon, or the frequency of the electromagnetic wave that corresponds to that photon. So, fairly simple equation, E equals hf. E is the energy of the photon, and you'll notice that given that it's energy, it's measured in joules, so you need to convert from electron volts to joules in order to use this equation. H is known as Planck's constant, so that has a specific value, and that value is 6.63 by 10 to the negative 34 joules seconds. And that particular quantity is stated in the data booklet. So it's a constant, it's basically a fundamental constant of the universe. And F is the frequency of the photon. And the frequency of the photon is measured in hertz. And remember, hertz is the same as per second. So there's the equation that we can use. We also know though that we have another equation where frequency is involved, and that's C equals F lambda. So looking at the speed of light being equal to the frequency multiplied by the wavelength. Now if we rearrange that so that F is equal to C on lambda, we can therefore say that E is equal to HC on lambda. So substitute that in for F. That has been rearranged in the data booklet. We can then figure out exactly what the wavelength is if we know what the energy level transition is. So that's the form of the equation in the data booklet. Lambda is equal to HC on E, where lambda is just the wavelength of the light. So I'm not going to bother notating that. And wavelength would be measured in meters there. Usually we'd express the wavelength for visible light in the nanometer scale, so 400 to 700-ish nanometers. Now, if we consider that for hydrogen, that we have all of these energy level transitions, we can represent that on an energy level diagram. So you'll notice on this diagram we've only got the energy levels indicated, so n equals 1 through to n equals 7. Haven't got the energies that are associated with them because we're not really worried about the energies here. We're just looking at the what the transitions themselves are. Now, with this diagram, you can see that we've got different series indicated here. So the Lyman series is basically any transition down to n equals 1. Balmer series is any transition down to n equals 2. The Paschen series down to n equals 3. The bracket to n equals 4. There's the Fund series down to n equals 5, and so on and so forth as well. Now, if we went through to identify what the wavelengths are here, what we would see is that anything from the Lyman series ends up being in the UV spectrum. So the frequencies of the photons that are emitted there would be in the UV spectrum. The Balmer series, these four here, they end up being in the visible spectrum. And then for the Paschen bracket and anything higher than that is in the infrared spectrum. So that means that if we were to look at the photons of light that are being emitted from hydrogen, there's actually only 4 that we can see with our eyes, but we'd be able to detect the others in the infrared and UV spectra as necessary. It also then means that we have these 4 visible lines that correspond specifically to hydrogen. So we need to just make a note there that each element, we've only really been dealing with hydrogen, but each element has its own distinct sequence of energy level transitions, and as a result that means it has its own distinct sequence of wavelengths. So that means that we have then a spectrum that we can refer to for each individual element. They're known as emission spectra. So emission spectra being the plural. For one particular element we talk about it spectrum. So these emission spectra are sort of a fingerprint of the element. And so that basically means that if we can observe the light that's coming from a particular substance, not being reflected from it, but actually being emitted by it, we can then determine what element it actually is by comparing it to its known emission spectra. So to give you a bit of an idea, we'll just have a look at some emission spectra for different elements. You can see here we've got hydrogen in the middle. Talked about the 4 visible lines that it emits, so 1 in the red, 1 in sort of the blue, and then 2 in the violet. Sodium also has its own, well, all of these elements have their own emission spectra. Typically these 2 here are the brightest for sodium. The other 5 that are shown there don't have quite the same intensity, and usually just see sort of 2 yellow lines. Calcium, you can see, has quite a few more. Mercury likewise has quite a few as well. Now we'll have a look at a few of these emission spectra in class. We've got a device that allows us to look at the emission spectra for different elements. Some are better than others, some have got more clearly defined lines than others, but still quite useful to be able to distinguish between them. Keep in mind also that these lines, when you view them on this sort of spectrum, you can distinctly see what they are, but if you were to look at the light coming from a source of, say, a sample of hydrogen gas, you wouldn't see those individual colours. You'd see them grouped together or mixed together, and so you'd see sort of a one single colour. So sodium tends to be a little bit orangish in colour because of the dominance of these colours here that are emitted from sodium. So if you ever see a sodium lamp, it'll be that sort of more orange colour. Now the flip side of this is that while we've got emission spectra, we have a sort of have the same sort of situation but in reverse. So if we were to shine white light, so white light being that spectrum at the top, all of the colours of the rainbow. So when white light passes through an element in its gaseous state, so it doesn't really work when it's a solid, we need light to be able to pass through it. Can work when it's a liquid, but we'll just deal with the gaseous nature, largely because this sort of thing is you usually vaporize a substance of whatever it is you're looking at in order to try and determine what it's made of. In that situation, it will only it'll absorb only specific wavelengths. So it'll absorb those same specific wavelengths. And that means that we have an absorption spectrum instead of an emission spectrum. So we'll have a look just at the absorption spectrum for hydrogen. So we can see there we've got the hydrogen emission spectrum on the top, and the emission spectrum is basically dark background with the specific wavelengths that are emitted, whereas for the hydrogen absorption spectrum we've got a rainbow background where we can see all of the colours of the light that are travelling through and that aren't interacting with the hydrogen at all, and then we get these dark bands, these four here, where those wavelengths of light are being absorbed by the hydrogen. Now the hydrogen atoms themselves would re-radiate those photons, but they would then be in a different direction, so it means that the intensity of light that's coming straight through the sample of gas is going to be much lower in those four specific wavelengths. And you'll notice that those dark bands line up with the same wavelengths for the emission spectrum. So as I said, we'll have a look at a few of these in class, the emission spectra, and maybe do a few calculations to see if we can figure out what the specific energy level transitions are.